In this video, we're looking at sign diagrams of the first derivative. Now, it is possible to draw sign diagrams of f, f dash, and f double dash, but we're just going to look at the derivative for now. Now, basically, sign diagrams will look something like this for the first derivative. The numbers that end up going here are your stationary points, so wherever it's flat. And then the pluses and the minuses will represent your slopes. So you can see this one, for example, this graph is flat at that value A. It sloped up until A, and then it sloped down after A. So that's what the sign diagram sort of looks like in context of the function. All right, so pretty much what you do is you have a function like this, and the goal will be to draw a sign diagram. So I've written out some steps to help us. Basically, step 1 is to find the derivative. So we'll do that. F dash of x. Out of this function, it's going to be 4x cubed plus 6x squared. Now, step 2 is to set the derivative to 0 or find where it's undefined. So we're going to set this to 0. Now, often when you're setting things to 0, you're looking for common factors. So I can spot that 2x squared here is a common factor, and I'd be left with 2x in that first term plus 3 in that next term. So just like that. All right, now that we've got this, we can start setting this to 0 a bit more effectively. So we use the null factor law. Either x squared equals 0, that would tell us that x is 0, or 2x plus 3 equals 0. So 2x would have to be minus 3. So that tells us that x would have to be minus 3 all over 2, just like that. So those are the two values that we call our critical points. And basically what we do with these critical points is we put them on the sign diagram. So let's have a look at our sign diagram. So there's x and there's f dash of x. So we put these 2 points on. Put x is 0 and then x is minus 3 halves, just on a number line like that. And conveniently, I have also graphed the function before on a calculator. So just be really clear what I did there. I went into graph mode. I typed the equation in there, drew it, and you can tell that there are 2 spots where it's flat. If I just sort of trace it at 0, you'll see that it's highlighting that flat bit in the middle there. And if I trace it, well, if I find my minimum with gsolve, you'll see that that minimum is at minus 1.5. So those 2 numbers on the sign diagram tell us where it's flat. Now you can actually just look at your function here. So it's sloping down up until that point. So you're going to put a minus. Then in between these 2 points, minus 3 halves and 0, it's sloping up between those 2 points. So you put a plus. And then it's sloping up again after the point 0. So it sort of slopes up, goes flat at 0, and then slopes up again. Now, that's one way that you can get the pluses and minuses on your sign diagram. The other way that you can do it is by picking a value. So, for example, in this range, I could pick, for example, x equals 1 is in that range, and then I could plug it into the derivative. So f dash of x was 2x squared with 2x plus 3. That's what we learned from that bit there. And if I plug in f dash of 1, I get 2 lots of 1 squared, and then 2 lots of 1 plus 3. Now, I don't really care too much about what the actual number is, but I know that's positive, which is why I put a positive there. So there's sort of the 2 methods that I've explained in this little thing here. So you can fill in the pluses or minuses. There's 2 ways to do it. First way, you look at the slope on the graph, or the second way is by plugging in a number and seeing if it's positive or negative. The function that you plug it into is the function that you're making a sign diagram of. We're making a sign diagram of f dash, that means we plug it into f dash. Now, I'm not silly, I well and truly understand that we're probably just going to look at the slopes to fill in these numbers, and that's fine pretty much all the time. All right, next we're going to state when f of x is increasing and decreasing. So it's decreasing wherever there's minuses on this sign diagram. So f of x is decreasing when x is less than or equal to minus 3 halves, and f of x is increasing when x is greater than or equal to minus 3/2. A couple of things. You might notice that it is both increasing and decreasing at minus 3/2. That's actually fine, because the definition of increasing is that the derivative just has to be greater than or equal to 0. So technically, if I have a function that sort of looks like that, where it keeps going flat, this function is always increasing, even at these flat bits, even there, by definition. If you want to talk about it not being able to be flat, you use the word strictly. So it's strictly increasing if the derivative is strictly positive or strictly negative. So for this graph, for example, basically what we've said is that this whole range back there, so that little section there, is where it was decreasing, so going downhill, and then the section up here is where it's increasing. Now, if we want to be really, really cheeky, technically, it's also decreasing at x equals 0, that single point, because it's flat at x equals 0. So you just have to be very careful about that definition. All right, find and classify all stationary points. So the stationary points are minus 3/2 for the x value. That's one of our stationary points. And the other stationary point we had was 0 on the x value. So those just came straight off our sign diagram. And basically to get that, you just plug in minus 3/2 to the function. So you could take minus 3/2 and plug it in for the x value there. But if you've already got this graphed on your calculator, you can just go trace and you type in minus 3/2 for x, and you're going to get minus 0.6875. Now, since we're in fraction land, I should probably stay doing fractions and not like mix my fractions and decimals. So let's see if we can get this, 6875. And then if we just hit S to D, that should give us a nice fraction, minus 11/16. So be consistent, give all fractions or all decimals, but try not to mix and match. This stationary point here, this is a local minimum. So I'm hoping local minimum there is pretty self-explanatory. Local minimums look like that. They look like the bottom of a valley. If you have something called a local maximum, that looks like the top of a mountain. Now the other two stationary points you can have are these types, the inflection points. That's where it sort of goes flat, but then keeps going uphill, or goes flat and keeps going downhill. So you can tell from the sign diagram, you can also tell from the graph. Notice how the minimum graph was minus plus. We had a minimum there, and on our sign diagram, it went minus plus. We've got this next bit which goes plus plus. We can sort of see that it's that flat sort of inflection point there, and it matches this sign diagram here, the one that says plus plus there, and that is a stationary point of inflection. So that's our next point. So this next one is a stationary point of inflection. Wonderful. We can figure out what the coordinate is. So if you want, you could plug in and find f of 0 to find that y coordinate, which would be 0 to the 4 plus 2 lots of 0 cubed plus 1. Or in other words, that's 1. Or what you could do is you could just trace. So you've already got it graphed on your calculator. We'll just go back up into that graph here. Draw that. And you literally just need to go shift trace and then type 0 for the x value. There we go, y is 1. So when you're finding and classifying stationary points, make sure you give me the coordinates, not just the x value. And you're classifying stationary points as one of these three things: local max, local min, or stationary point of inflection.